Right, so as was said, I'm going to be talking about statistical mechanical mappings for quantum codes with correlated noise. This is joint work with my supervisor, Steve Lemire in Sydney. And this paper is on the arXiv if you want any details, or come talk to me in one of the breaks. So when studying quantum codes, there's sort of two main questions that might come up for a given quantum code. The first is a more practical question of, given a quantum code, how do I decode it? Decoding a given code, even if it's a sort of good code, it isn't always the most obvious thing to do. And the more theoretical question you might ask is, how good is the code? For example, what is the threshold of that code? And roughly speaking, today's talk is going to be addressing techniques for answering both of these questions. Moreover, you can slightly complicate both of these questions, of course. You can ask not just, how do I decode, but how do I decode optimally, or approximately optimally, or something like that. And you could even ask more complicated questions like, well, I don't just care about a threshold under optimal decoding. What about if I need to deal with faults? I have measurement errors, I have gate errors, things like this. So you can ask more complicated questions about the performance of your codes. And so, at least for stabilizer codes with Pauli noise, one of the most powerful techniques that we have, and this is by no means a new technique in general, it's been around for almost 2 decades, but one of the most powerful techniques we have for studying these questions is something called the statistical mechanical mapping. And today we're going to sort of be looking at generalizing this mapping for slightly more general codes and more general noise models, and better exploring exactly what sort of features of codes you can actually extract by using this mapping. And one thing I should say, I'm going to stick to stabilizer codes on qubits for today's talk, but it generalizes to subsystem codes for qubits. That's just for notational clarity. Okay, so to be slightly more specific about what's the idea with the statistical mechanical mapping. So generally, the idea is going to be that we start with some code and some understood noise model, and we're going to map that over in some sense to a statistical mechanical model. So as we'll see, the Toric code under a certain setting will map over to something called the 8-vertex model, for example. And the rough idea with this mapping is, and again, I'll make this more rigorous as I go on, but the idea is that the error-correcting properties of my code are going to directly relate to the thermodynamic properties of the StatMech model. That isn't just going to be a sort of rough qualitative statement, it's also going to be a quantitative statement. And so you'll be able to extract properties of the StatMech model and leverage the fact that there's a whole bunch of literature on how to study these StatMech models, both analytically and numerically, and pull these results back and learn things about your StatMech model. Okay, so to be slightly more specific about what sort of features we're going to be able to get out, so we start with some stabilizer code with Pauli noise. This is going to map over into a disordered statistical mechanical model. It's a disordered system, so it's not the nicest system to deal with, but there are ways of studying these systems. The two main properties that you get that map over, number one, that the threshold of this code, there are some assumptions that I'm missing out on here, but this is the rough idea, that the threshold of this code is going to directly relate to a phase transition point in the StatMech model, and that's a bidirectional thing. So by studying the phase transitions, you'll be able to actually estimate the threshold of this code. And in fact, this is one of the main features of this mapping that it's often used for. Another feature that's often sort of overlooked is actually you can also show that decoding this code is equivalent in an appropriate sense to calculating partition functions over in this StatMech model. So yeah, as I sort of was getting at, you could take, pick your favorite method for estimating phase transitions over in the code, let's say Monte Carlo simulations, and I'm going to give an example later. You can take those simulations basically as a black box, and that would give you a way of doing threshold approximations for the code. In a similar way, if you have any way of calculating, or in practice probably approximating partition functions, you can use that to give you a decoder, which I'm going to talk about at the end if I have time. Okay, so just a quick overview of our results before we get into it. So the first is, probably the main result is that we show how to generalize this to correlated noise. So up until now, Mostly the StatMech model has actually just been considered for examples, so it was originally considered for the Toric code, it's been considered for the color code, even some non-topological codes. But we're going to show how you can actually generalize this for any code. That's not so surprising, but also for correlated noise. Up until now, it's only been considered for mostly IID noise. By way of example, to show that the sort of calculations you can do in this, we're going to look at some mild local correlations in the Toric code and do a threshold calculation and show that even relatively mild correlations can change the threshold quite a bit. So again, if I have time, at the end I'm going to get to showing that you can actually use this relationship between decoding and partition functions to actually get a tensor network maximum likelihood decoder, which, as it turns out, is actually, it ends up being a generalization of the so-called MPS decoder of Barbie, Suchara, and Vago for the Toric code to more general codes and correlated noise. And then something I'm actually not going to have time to talk about today, but if you're interested, definitely come ask me about it. We were able to also show how you can consider, so I mentioned correlated noise here. I'm mostly going to talk about spatial correlations. But we also showed how you can also treat spatiotemporal correlations. So if you have noisy measurements, for example, in multiple syndrome extraction rounds, that will give you space-time correlations. We actually give a construction where you essentially bolt another dimension on corresponding to time, and that gives you a way of actually modeling that as well using this mapping at the cost of an extra dimension. Right. Okay, so this slide should be largely not necessary at this audience, I would expect. Whenever I say Pauli, I mean Pauli up to Phys, stabilizer code, whatever. The only piece of notation that maybe is not entirely standard that I'm going to use, I'm going to talk about these logical error classes. So here E is a Pauli. Whenever I write E bar, I mean all of the Paulis that are stabilizer equivalent to E, just as a piece of notation. Okay, so I'm going to start. I'm going to start with the independent case. So what I mean by that is considering independent noise acting on all my qubits. This construction is largely known, but I'm gonna write it in a slightly different notation than it's usually written, because it turns out doing so is going to allow it to be extended to the correlated case relatively straightforwardly. So one piece of slightly peculiar notation is this so-called, we call it the scalar commutator. So this double-struct commutator. Here A and B are Paulis. This thing is +1 if they commute and -1 if they don't. Point is this is a number, not an operator, so it satisfies that equation. Right, so this is the mapping in the independent case. So there's a bit to unpack here, so I'm going to sort of try and point out some features. So to start with, you start with stabilizer code with stabilizer generators, capital SK. We have some Pauli error E. The E here is going to take the role of the disorder in our Hamiltonian. So for each E, we have a Hamiltonian. The degrees of freedom in our Hamiltonian are, because we're doing qubits, they're plus or minus ones, and they correspond to the stabilizer generators. So the states correspond to elements of the stabilizer group in that way. So the Hamiltonian takes this form. So the first thing to notice is that each term in our Hamiltonian, so Pi here corresponds to the Pauli group on an individual qubit. So this is a sum of a single qubit Paulis, right? So each term in the Hamiltonian corresponds to a single qubit Pauli. The first term, there's just a scalar term, the coupling strength. I'm going to come back to that in a few slides, but that's just some constant. The second term is the effect of this, the disorder part, the E here. Remember that this is just a plus or minus 1. So the effect of the disorder will be to flip some of the terms in the Hamiltonian. I'll sort of come back to that as well. And then finally, we actually have the degrees of freedom, the actual, what parts are coupled. So which spins are coupled. So first of all, this is just a product of spins. So in that sense, it's a sort of Ising type Hamiltonian in a sense. And then which spins are coupled depends on the commutation between the stabilizer generators and this single qubit Pauli sigma. Okay. So three sort of features to notice. First is it's sort of Ising type in the sense that it's a sum of products of spin terms, where each term, as I said, corresponds to a single site Pauli. The disorder simply flips some of these terms from ferromagnetic terms to antiferromagnetic terms. And finally, because of this the nature of this term here, if we started with a local code, our StatMech model is going to be similarly local, right? So if I started with a local 3D code, this will be a 3D StatMech model with similar locality. Okay. So you might ask, okay, well, why do we construct the Hamiltonian in this way? So this has a rather important symmetry, as we'll see. So by sort of expanding out the definition, you can see that this scalar commutator has this sort of multiplicative property. And a consequence of that is that this Hamiltonian actually has a gauge symmetry naturally built in, which nicely corresponds to the stabilizer generators. So here, if I take an individual spin within my system, I flip that spin, but then I also apply a stabilizer to the disorder, that's a symmetry of the Hamiltonian. So, one example of something like this, as we'll see, imagine I have an Ising model. If I flip any spin, but then also flip all of the bonds to that spin, that's always going to be a symmetry. Right? And this is the sort of same idea, except now I'm naturally sort of, I've built the stabilizer group in as part of this gauge symmetry. And that's actually going to be quite important. One of the immediate consequences of this is that if I were to look at the partition function of these disordered Hamiltonians, because of this symmetry, I straight away get that any two disorders that only differ by a stabilizer necessarily have the same partition function. That's also going to be a nice property going forward. Right, so I mentioned early on that we're going to consider independent noise. I haven't brought up the noise yet, so let's bring that in. I also haven't told you the coupling strengths, which is going to be related. So we have an independent noise model, by which I mean that the probability of some Pauli error E can simply be modeled as a product of the marginal probability rates on each qubit. So here I corresponds to a qubit. EI is the action of E on qubit I. And what we're going to want is that the partition function, I said here that the partition function is sort of, invariant up to stabilizers in this way. Specifically what we want is that the partition function reproduces these logical class probabilities, right? So the probability of any error that's logically equivalent to E. It turns out this connection actually implies quite a lot. This is the sense in which it links the thermodynamic properties of our StatMech model to the error correction properties of our code. The way I sort of think about it, when people talk about StatMech models, they'll say, well, the partition function basically encodes all of the thermodynamic properties. The error class probabilities, I think, can be thought of in a similar way for a code. Right, so this is the expression that we want. How do we get this? Well, first of all, we can use the gauge symmetry to re-express, so this is just the definition of the partition function. Here we have a sum of states. We can use that gauge symmetry from before, which lets us flip the states and change the disorder. So we can change that into a sum over disorders now, but that is just by definition a sum over this logical error class now of the Gibbs weights in the all plus one state. And so now all we need to do is we need to pick our coupling strengths such that this Gibbs weight corresponds to the probability of an individual error. If that's true, then by this expression we will necessarily have that the partition function reproduces the class probabilities. Okay, so can we get that? Well, this is the expression that we want. We re-express this. We actually plug in the Hamiltonian. You take a log, you get this expression. Again, it's not necessarily clear whether such J's exist and whether we can figure out what they are efficiently. Rather nicely, you get this sort of Fourier-like condition. You can sort of think of this as like a Fourier transform, so you just sort of do the opposite. You do an inverse Fourier transform. And you end up with this thing that we call the Nishimori condition, which essentially says that our J's in this sense are just the Fourier transform of the log probabilities, which is quite nice. And so the long and the short of it was that this then implies that the partition function reproduces the class probabilities. Yeah, and as I said, this is the sort of intrinsic link between the thermodynamic properties of the StatMech model and the error correction properties of the code. Okay. Good. So as a bit of an example, I'm going to go through the original construction for the Toric code, because I find a lot of people, when talking about the StatMech model, get a bit confused about exactly how the construction works and what lives in what space. So, okay, we're going to start with the Toric code with IID bit flip errors. So we have our lattice. We put the black circles here are qubits. We put our qubits on the edges. So So this is one thing that people often get confused by. Because we're considering bit flip errors, a lot of people think, well, okay, I only need to consider the Z-type plaquette operators, right? Actually, you want to consider the X-type star operators, because the thing that matters is, I mean, the plaquettes are the things that measure our syndromes, but the X-type stabilizers here are the things that give you the equivalence between errors. Okay, so IID bit flip, so the probability of an X error on any given edge is P, probability of identity is 1 minus P. So the first thing that we do is we have a spin. I said we had a spin for every stabilizer generator. Stabilizer generators live on vertices now, so we put a little blue circle. These are our classical spins on every vertex. Next, we want to look at the interactions. So each interaction, I said, was induced by a single qubit Pauli. So now we consider some single qubit Paulis. So first of all, I could consider just an identity sitting somewhere. Well, the thing that matters is that single qubit Pauli will couple all of the spins corresponding to stabilizers that anti-commute with that Pauli. Well, the identity anti-commutes with nothing, so it doesn't do anything. It's a constant term in the Hamiltonian. I'm just going to ignore it. Similarly, because I only have to consider X-type stabilizers, a single qubit X, again, commutes with everything of relevance here, so that also does nothing. Any single qubit Y or single qubit Z will anti-commute with the two neighboring stabilizers. So this Y term here, for example, will induce a coupling like that, and a Z will introduce a coupling like that. You do this on every qubit, and you end up with an Ising type model, coupling horizontally and vertically between nearest neighbors. But here we didn't consider disordered. This is sort of the ordered version of this Hamiltonian. And so now to consider disorder, we don't just look at the commutation with the stabilizers, but we look at the commutation with the error times the stabilizers. And the effect of this is that whenever we have an error on any, so let's say this vertical, this qubit here on this vertical edge here had an error, the effect will be that it will introduce a -1 here to flip that corresponding bond from ferromagnetic to anti-ferromagnetic, okay? So in the case of no error, we would just have a ferromagnetic Ising model, but the errors will flip these terms, okay? And now we take away the code to just leave the StatMech model, and what we're left with is what's called the random mod Ising model. In this case, the plus or minus J random mod Ising model, meaning that the coupling strength is always fixed, it's just the sign that flips. And so in this sense, we can think of now the error model as saying, telling us about the probability of the sign of our bonds, right? So this is actually a relatively well-studied StatMech model, which is quite handy. Okay, so just to give some other examples, so here we looked at the Toric code. Bit flips give us the random mod Ising model. By symmetry, if I had phase flips, I'm also going to get a random mod Ising model. If I had independent X and Z errors, I'm actually going to get two uncoupled copies of the random mod Ising model. So I get this sort of blue sublattice living on the vertices with coupling between them. And then I get a red sublattice living on the plaquettes with Ising type couplings there as well. But the two sublattices don't actually couple together. That's actually replicating the fact that, in this case, if I have independent X and Z noise on the Toric code, I can separately correct X and Z errors, right? So that's not too surprising. And then for depolarizing noise, for example, when I can't just decouple them, you actually get a four-body coupling between the layers. And in an appropriate sense, this is related to a randomized version of the 8-vertex model. And then you can do a similar sort of thing for the color code. It's very similar, but you end up with like three-spin Ising type terms. Again, you get the two sublattices, and then depolarizing couples them. Okay, so that's a rough idea of how these constructions go. Right. So I mentioned earlier that one of the key features about this is that we directly get to relate the threshold of our code to a phase transition in the StatMech model. And so I'm not going to give a proper rigorous proof here. There's a few assumptions that I'm going to sort of brush over, but this is to give at least a little bit of a sketch as to why this connection exists. So one way to see it, why it exists, is to consider the free energy cost of introducing a logical error L. So this might be a sort of weird quantity to consider. So if you were to consider the random mod Ising model, this would actually correspond to, because logical operators in the Toric code correspond to strings, if I were to ask about the free energy cost, this will actually be the free energy cost in that system of a domain wall being introduced, right? So you can sort of think of this as a generalization of a domain wall free energy. Right, so this is the free energy when the disorder is EL and the free energy when it's E. I've expressed this explicitly in terms of the partition functions because we actually know that at least when the Nishimori condition is satisfied, we have this expression. So now this free energy cost just becomes, okay, ignore the temperature term, becomes a log likelihood ratio of these class probabilities. And what that actually implies is that if we're below threshold, in which case for a given syndrome, all of the probability is masked on a single logical error class, that'll actually imply, it's actually equivalent to, I should say, the fact that this free energy cost diverges to infinity. And similarly, above threshold, when I can't error correct, this free energy cost actually goes to 0. There's a bit of subtlety in exactly what sense these converge, but that's at least the idea. And with some assumptions, you can actually make this correspondence rigorous. So this is the idea of why these two things are related. And so the sort of sketch that you get, and for most of the systems that have been studied numerically, this I say sketch, this is pretty much exactly what they look like, and we'll see some numerics in a few slides. The rough idea of what you end up getting is, so here we have, this is meant to be the phase diagram of our disordered system. So here we have the temperature, and here we have some noise parameter. In general, there could be more than one noise parameter. I've just drawn one for clarity. So in the random mod Ising model, this would be temperature, and this would be the probability of me having anti-ferromagnetic bonds. These systems will typically have some ordered region for low temperature and low noise, and then a disordered phase outside of that. This is the Nishimori condition. And then the point at which the Nishimori line crosses the phase transition, the Nishimori point you might call it, that point, if you drop that down into the noise parameter, that exactly corresponds to the threshold of the code. Okay? This is the threshold under optimal decoding. It turns out actually you can, in an appropriate sense, you can interpret this entire boundary as thresholds of suboptimal decoders, which is sort of nice. For example, for this point down here actually corresponds to the so-called minimum energy decoder. For the Toric code, that's the minimum weight pair matching threshold, which is sort of nice. But anyway, for the most part, you usually only are concerned with this, the optimal threshold here. The fact that this corresponds to the optimal decoder actually means that the point at which the Nishimori line crosses is always the furthest right point on this phase transition. Yeah, and then the rough idea is that this region corresponds to the ordered region where error correction is possible, and then this is disordered where it's not. Yeah. Okay, so up until now, I've just been considering independent noise. So now we're going to move on to the correlated case. So as I said, the way that we laid out our notation is actually going to make this jump relatively smooth. So, you know, what feature of the independence did we actually need? Well, the key thing that we needed is that our probability distributions can be factored out into local pieces in this way. But it doesn't actually have to be strictly independent, and so we can actually relax this a little bit. So this relaxation we refer to as factored distributions. The idea here is that as long as it factors out into local chunks, I don't mind. That's the only property that I need. And so what we can consider is, suppose I have some regions, Rj. By regions, I just mean subsets of qubits. And you should think of these Rjs as overlapping, right? If they're not overlapping, it's just independence. But if they're overlapping, it's a strictly bigger thing. So for example, these regions could be all nearest neighbor pairs of qubits, for example. So now I have some overlapping regions. And all I need is that my probability distribution can be factored into functions from the Pauli groups on these regions to the real numbers. I suppose these can be non-negative reals, but that doesn't really matter. I have some of these local functions, and my full distribution just factors into these local pieces. Okay? And as I say, if these are overlapping, then they no longer can be considered just to be the marginals. They're more complicated things. But yeah, that's the idea. And I should say, I mean, this is a relatively broad family of correlated noise models. Yeah. So this includes a lot of graphical models like Bayesian networks, Markov random fields, Gibbs random fields, things like that. Okay, and so the construction actually works very similar to the previous construction. Here we just change single qubit Paulis to single region Paulis. Okay, so this was previously a sum of Paulis living on a single qubit, now it's single region. Other than that, it's the same. Similarly, this is now a Fourier transform over this this regional Pauli group instead of a single site Pauli group. And all of the proofs and arguments I gave before extend exactly the same, which is quite nice. And so this argument about the partition function and the phase transitions also holds. The effect of including these correlations is essentially to include longer range terms in the Hamiltonian. Okay? So if I have correlations between, say, these two qubits, I now get this diagonal term in my Hamiltonian. If I have correlations between, say, these two qubits, I get a four-body term. These two qubits, I'm going to get a longer range term. Ignore that. Yeah, it still works. Right, and so so we did some numerics to look at a specific model. The idea here is we looked at correlations across plaquettes in this way. This model can be entirely described by these four conditional probabilities. So the idea here is that an error occurring here makes an error here more likely. You can parameterize this by two parameters, the marginal error rate and this correlation factor. And so we did some Monte Carlo simulations to actually look at where the phase boundary for this is. So this blue line is some previously done numerics by some StatMech people. This in principle has error bars on it, but they're like smaller than a pixel, so I just drew it as it is. This point here will then correspond to the bit flip Toric code in the IID case, and then with some mild correlations, this is the threshold we found. And essentially it drops from roughly 11%, 10.9% to roughly 10%. Okay. Right. So I'm just going to quickly talk about the decoding, depending on how much time I have. Yeah, okay. Right. So I talked about giving thresholds. You can actually get out useful decoders from this as well. So the idea here is that whenever you're doing decoding, you can think of this as I've measured the syndrome of my error, and then from that I get a list of logical error classes that my error belongs to. I don't know which one. And if I wanted to do optimal decoding, I want to then calculate which of those error classes was the most likely, and then that's the class I'm going to assume that my error was in, right? This is the so-called maximum likelihood decoder. So the hard part of this decoding is essentially calculating these logical class probabilities, right? Because this logical class, for a topological code is going to be exponentially large. So calculating these probabilities is very difficult. But we know that these logical class probabilities we can re-express as partition functions of our StatMech models satisfying the Nishimori condition. So this gives us a natural way of re-expressing the problem of maximum likelihood decoding in terms of calculating partition functions. We'll get back to the issue of whether we can do that efficiently in a second. So the general sort of strategy here would be I measure my syndrome, I construct some error with the correct syndrome. I don't care if it's a particularly likely error, just some canonical choice of error. I then approximate or calculate or whatever I could do the partition functions which give me the logical class probabilities of all the relevant classes. I then pick the L that gives me the largest, and then I apply the corresponding error to correct. Okay. So this is all good and well. This is hard to calculate. This will also be hard to calculate in general. It'll be sharply hard to calculate these things for 2D systems at least. But at least in 2D, there are some relatively natural ways you might go about approximating these things, at least numerically. So there's sort of half a dozen techniques. One that we looked at was correspondence between partition functions and tensor networks, relatively well understood connection at this point. One of the nice things that you can do, so this gives you a way of writing out the partition function in terms of for a 2D system, in terms of a 2D tensor network. And then we can use what's usually referred to as MPS, MPO, approximate contraction. So the idea is I have some 2D grid. I take this column, I treat it like an MPS, I contract it in to the next column, and then I use MPS truncation as an approximation to trim it back down, and I keep going. So this gives you some controlled approximation scheme to attempt to evaluate the value of this. And rather nicely, if you take this, so this in principle gives you a way of doing approximately optimal decoding for any 2D code with local correlations. One rather nice thing, if you plug in the Toric code with IID noise, you exactly reproduce the Bravi and Suchara and Vargo decoder. Even up to like, even the tensors are the same. It's not even the same tensor network, it's like exactly the same network, which is sort of nice. Okay, so today I've talked about how you can extend the stat mapping to correlated models. We've shown at least some relatively primitive numerics that you can do with this to get out the effect of correlations on thresholds. I've also shown how you can actually use this to give maximum likelihood decoders. Actually, David Tuckett is going to talk a little bit about using these decoders on Friday. We also looked at, so some obvious questions that you might ask is, can we actually apply this to, the correlated noise model that we studied is somewhat contrived. You might ask, can I actually use this to extract thresholds for, experimentally motivated correlated noise models? You can also ask if you can extend this to other codes. There are some extensions we can sort of do, at least on a formal level, but interpreting them is sort of tricky. You could also ask about non-Pauli noise, non-stochastic noise, coherent noise, things like this. And then another natural thing is to look more generally at the relationship between what different kinds of correlations, what effect different kinds of correlations have on the threshold. And we have some numerical work looking at that at the moment. Thank you.
Great, we have time for a few questions.
Hey, thanks for the nice talk.
Thanks.
You showed this phase diagram, this phase diagram, and you mentioned that on the 1D phase boundary,
you
have like a family of decoders with the maximum likelihood at the outermost point, at the minimum energy, at the process. So, do you understand like this kind of interpolation between these two?
Yeah. So what the decoder is. Let me see if I remember it correctly. So instead of basically, you take this decoder I described here. So, okay, imagine instead of writing a partition function here, I wrote a free energy. Okay, that's the same optimization. But then I suppose I optimize that free energy, not necessarily at the Nishimori point. Okay, so essentially the idea here is, so you can consider what you might call the minimum free energy decoder, where I pick a temperature, and then given that temperature, I then minimize the free energy in a similar way that I was doing with the partition function. If you do that here, that exactly reproduces the maximum likelihood decoder. If I do it down here, so the zero temperature limit is just minimizing the energy, not the free energy, that exactly reproduces minimum weight pair matching. More generally, this whole line will be the threshold of that decoder, right? And depending on what the temperature is, at this temperature it's optimal, otherwise it's some suboptimal decoder. You can sort of think of it as, there's sort of an entropy term and an energy term. So like down here, I'm just saying, find me the single most likely error. I don't care about error classes, just error, right? Minimum weight pair matching. So there you're sort of completely ignoring what you call entropy in the StatMech sort of universe. Here you're perfectly balancing the two so that you're doing the optimal thing. And this is sort of naturally interpolating between them. What like that means, for example, and some other things, I don't know. And you also get, I suppose you can see it in the numerics, you get some weird stuff where like, this comes up and comes back down. So there's a decoder here that doesn't work for low error, then starts to work as you increase the error and then stops again. What that means, I don't know, but yeah, you get some weird stuff coming up here. Yeah.
I was just wondering how specific this duality between the error correcting codes and StatMech models is to Stabiliser codes, or can you also push it beyond stabilizers?
Do you have something in mind?
Let's just abstractly, a quantum error correcting code, but that satisfies error correcting conditions, but not necessarily Stabiliser codes.
Yeah, no, this is something we're definitely interested in. It's unclear. So, like, yeah, so we can extend it to some things, at least on a formal level. Then interpreting what you can get some correspondence, but then the thing that you get out won't be these nice. The main thing that you might lose is this natural notion of like a logical class probability, right? If you're not necessarily looking at stabilizer codes, that's not necessarily a thing that you have, right? In a very abstract model, that's not really a thing, right? That tends to be the thing that you lose. So you might get some correspondence between some quantity in the StatMech land and some quantity in the code, but that thing might not necessarily be all that useful. That seems to be the main issue. So one thing that we've looked at that has a similar mathematical structure is extending this to more general quantum doubles. So what we've done here is essentially abelian finite quantum doubles. You can do it for infinite abelian quantum doubles. I don't know how to interpret that. You can sort of do it for non-abelian quantum doubles, but again, the interpretation is very weird. But yeah, no, that's definitely something we're interested in.
Thanks.
Yep.
Okay, let's thank Chris again.